The covariance between the returns of two assets. We have two assets here, 1 and 2, with the following returns. The covariance between the returns of assets 1 and 2 is given by the product of the difference, the simultaneous difference between each return and the expected return of each assets in every different state of the world. So we have calculated earlier that the expected return of 1 is 13.45. For the second asset, we have 10.70, and we also so from there we can compute the covariance between the two assets. So here I've put all the details. Okay, so first, state 1, 10%. In state 1 occurs with probability 10%. In state 1, asset 1 returns 24, asset 2 returns 14. State 2 occurs with probability 45%. In state 2, asset 1 returns 18, asset 2 returns 22, and so on. Okay, in state 4 occurs with probability 10%. In state 4, asset 1 returns minus 2, asset 2 returns 8. We always take the difference between each of the returns of asset 1 with the expected return of asset 1. We do the same with asset 2, and the result gives us like 53.69 percentage squared. Percentage squared, like the covariance itself, is like awkward to work with, so we prefer to normalize it. Because like the size of the covariance depends on the size of each of the variance of each of the assets we consider. So by taking the covariance and dividing it by the product of each of the standard deviations, we obtain a measure which lies always between 0 and 1. In this case, since we have for asset 2, if we calculate the standard deviation of asset 2, we obtain 11.62, which gives us a covariance between the two assets of 0.64. If we have many assets, more than two assets, we can always construct a covariance matrix and work with it. So the diagonal would be all the variances, and off the diagonal you will have the covariances. So consider a portfolio composed of two assets, 1 and 2. The proportion invested in asset 1 is identified with x1, and the proportion invested in asset 2 is identified by x2. The expected return of the portfolio is the weighted average of each expected return, and the weights are the proportion of each asset in the portfolio. And if we have more than two assets, we do the same exercise to compute the expected return. The variance of the returns of a portfolio. So the variance of the return is given by this equation here. It's the expected value of the return of the portfolio minus the expected return of the portfolio to the power 2. So the first line here is the basic equation for the variance. We develop the return of the portfolio. So x1 times r1 plus x2 times r2. So there are two assets in the portfolio. We develop expected return. So expected return of the portfolio is the x1 times the expected return of 1 plus x2 times the expected return of 2. But here we subtract the expected return of the portfolio. Now we move all the terms all the terms derived from asset 1 together, all the terms related to asset 2 together, and then we extract the x's, okay, and we put the x in front of a parentheses where we have the difference between return of each asset and its expected return. We explode the square, and this is what we obtain. Let's do it step by step. A plus b to the power 2 is equal to a squared plus b squared plus 2 times ab. A. So a is x1 o times r1 minus expected return of 1. So a squared plus 2 times, so x, and so the two terms are separated because I've put the x's together here. B. Okay, all good. We have the expectation of a whole bunch of terms which are added together. So the expectation operator is a linear function, so we can take the expectations of all the items separately. Now we take the x's outside of the expectation operator because we can. It's a linear function. And now this is the end of our calculation. So x1 variance, x1 squared variance of 1, x2 squared variance of 2 plus 2 times x1, x2 covariance of x1 and x2. So you have all the details here. So the variance of P is x1 squared variance of 1, x2 squared variance of 2 plus 2 times x1, x2 covariance of 1 and 2. But then we can rewrite the covariance in terms of correlation times the standard deviations. And if we compute the standard deviation of the portfolio return, we obtain this. If we have more than 2 assets in the portfolio standard deviation will be the sum of all the weights squared times the variance of each asset. Okay, plus 2 times every possible combinations of x1, xi, xj, correlation 1 and j, sigma 1, sigma j. All good? We have a portfolio of 2 assets. Expected return is this. Standard deviation is this. Now we'd like to construct a graph showing expected return as a function of standard deviation. So how can we combine these two equations together to obtain a function that describes expected return as a function of standard deviation and vice versa? So we have our 2 equations here. What do they have in common? X. Okay, so here I've replaced x1 by x and x2 by 1 minus x. So what do they have in common? X. So from the first equation, I can replace x by this. Okay, so if we play around with the terms, this is what you obtain. So you go and plug this in the second equation. This is what you obtain. And here's our equation. Okay, so if our 2 assets have the following expected returns and standard deviations, as well as the following correlation. So the function sigma p is equal to all these terms together, so we can write it down. So what will vary is, so expected return of B is given, it's 7.4. Expected return of A is given, it's 16.5. Variance of A, we have it over here. Variance of B, we have it over here. So what can vary is the expected return of the portfolio, and this will give us standard deviation of the portfolio. So here's the equation. So here's what the last equation gives on a graph. So we have expected portfolio return here, and we have standard deviation of the portfolio here. So this point here is 7.4 and 15. Okay, 7.4 and 15. This is asset B. This point here is 15 point. It's a 16.5 and 28. 16.5 and 28. This is point A. So if all the weights is in B, we obtain the expected return of asset B and the standard deviation of B. As we move slowly the weight towards A, we move towards the characteristics of A, which are 16.5% return and 28% standard deviation. But by doing so, there's still a point where we have a lower standard deviation than the lowest of the two standard deviations. Okay, so here this is what these are all the combinations, risk and return we can achieve by shifting the weight from B to A. Now we prefer having expected return on the vertical axis and standard deviation on the floor. Okay, so we're gonna shift, we're gonna rotate the last figure, and this is what we obtain as a characteristic of our investment market. So this is B. These are the characteristics of B. These are the characteristics of A. Here, 100% of the weight is in B. Here, 100% of the money is invested in A. And these are the combinations, standard deviation and return we can obtain by shifting money from B to A. So the previous figure imposes that the weights be non-negative. Okay, so we couldn't move away from B from the bottom or away from A at the top. But suppose you can do whatever you want. So the weight in one asset can be smaller than 0, and the weight in the other asset can be greater than 1. So this means, so when the weights are all above 0, what does that mean? So if you have $100 to invest, so some of it will be in A, some of it will be in B. Now, and the total money invested will be $100. If you allow for short sales, so if you allow to sell short one of the assets, well, you can invest even more than what you have in the other. So when X is greater than 1 in one of the assets, this would mean, so if I have $100 to invest and I short for $20 of asset 1, then I can invest $120 in asset 2. Okay, so X I greater than 1 means more than your initial wealth is invested in one of the assets. So this is what we can achieve if it's possible to sell short one of the assets. Okay, so as we move to the right hand side of A, so we always buy. So here we are all invested in B. Okay, so 100% in B. So now we reduce the weight in B, we increase the weight in A, and here we are 100% invested in A. So as we move from here to this direction here, so we are even more than 100% invested in A, which means that we sell short some of B to invest even more than what we have in asset A. We do the opposite. So here we are 100% invested in A. So we reduce the weight in A, we increase the weight in B. Here we are 100% invested in B. We keep moving. So we are even more than 100% invested in B, which means we sell short some assets A, and we invest the proceeds on top of what we have in cash in asset B. So here we have all the possibilities, okay, with different values for the correlation. So when correlation is perfectly negative, then it's possible to combine both assets, okay, to eliminate risk completely. And when the correlation is perfectly equal to 1, then the risk of the portfolio is the average risk of the assets in the portfolio. Okay, so here you have the details of what happens when correlation is -1, what happens when correlation is equal to 1. Suppose you have many assets to invest in. Okay, so all the assets here. So when you combine all the assets with all the different ways, in all different ways possible, there is a frontier which is the best combinations, risk and return you can achieve. So what is this? So for for a given level of risk, okay, so the blue line here gives the maximum expected return I can achieve by mixing all these assets in all possible ways. So A could be sold short, B could be purchased, C purchased, B sold short. I mean, the only constraint here is that the sum of the weights in all of the assets be equal to 1. Okay, so if I sum all the weights, it has to be equal to 1, but then like 1000% could be invested in C. Okay, and minus 10,000% could be invested in A. So you can do whatever you want as long as the sum of all the proportions is equal to 1. So this is the frontier of the best you can do for every possible level of risk or for every possible level of expected return. So if you aim at an expected return of 12%, well, the blue line gives you the combination of all the available assets you have to put in place, okay, in order to construct the portfolio with the lowest possible standard deviation. So here's like some more explanation of what I just said. So sigma is always the smallest attainable level of volatility for each expected return, and the expected return on the frontier is the highest return achievable for a level of risk. Okay, so suppose there is a risk-free asset, okay, and you can borrow and lend at the risk-free rate. Okay, so the risk-free rate means no volatility, so the variance of the risk-free return is 0. And the covariance of the risk-free return with any return is equal to 0, so there's no variance. And the expected return of the risk-free rate is the risk-free rate. Oh, good. So we have 3 assets plus a risk-free asset. What can we do, okay, with all these 4 assets? So all the assets here are on the graph, okay, and every number here is a percentage. So A has a risk of 22%, an expected return of 12%. B has a risk of 25%, an expected return of 23%. If we combine A with the risk-free asset, what do we have? So what's the expected return of a portfolio composed of A and the risk-free asset? So the weight in A is WA. So the expected return of the portfolio is the weight in F times RF plus the weight in A times expected return of A, which we can arrange as follows. So the risk-free rate plus the proportion invested in A times the difference with respect to F that A gives us. And what is the standard deviation of this portfolio? Well, if we compute the standard deviation of this portfolio, so since the standard deviation of F is always 0, it's simply the proportion invested in A times the standard deviation of A. So we have this standard deviation of the portfolio is WA times sigma A, so we can rearrange it, okay, to obtain a WA as a function of the standard deviation of the portfolio divided by the standard deviation of A, and which means so we can, in the expected return equation here, we can replace WA by this ratio. Okay, so if we replace WA here by this ratio, so we obtain the equation you have here at the bottom. So the expected return of a portfolio given by composed of A and the risk-free asset is equal to the risk-free rate plus this ratio here times the standard deviation of the portfolio. This ratio is called the Sharpe ratio. So the ratio expected return of the asset minus the risk-free rate divided by the standard deviation of the asset is the Sharpe ratio. So for the amount of risk you take when you invest in A, how much more than the risk-free rate do you obtain? Okay, so it's like your benefits of taking risk per amount of risk taken. So if we plug the expected return and volatility of A in the above equation, so we obtain the equation E of R is equal to 8 plus 2 over 11 times the standard deviation of the portfolio, and on the graph this is what the line looks like. So these are all the possibilities we can achieve by combining A and F. So below, on the left hand side of A, so some of the money is saved at the risk-free rate. On the right hand side of A, so we borrow at the risk-free rate to invest even more than what we own in A. And if we do the same with B and C, these are all the possibilities. So if there's only one of A, B, or C we can choose to combine with the risk-free rate, which one will we choose? Well, definitely we will take B. So B offers the best possibilities. So for any level of risk, whatever I can do with A, I can do way better with B. For any level of risk, whatever I can do with C when I combine it with the risk-free rate, well, I can do better with B. Okay, so B is the best. So B, and what is the characteristics? What is the one characteristic of B that tells me it's the best? It's Sharpe ratio. So B is better than all the two other assets because B has a higher Sharpe ratio. So B is the best portfolio to combine with the risk-free rate. All good? Suppose we go back to the market with many assets, and suppose we can combine all the assets in the market in whatever way we want. So that gives us the frontier we found that we derived earlier. Well, if anything to the right hand side of the frontier is feasible, so our best options will always be on the frontier. Okay, so it's impossible to go to the left hand side of the frontier. It's too good to be true. So on the left hand side of the frontier, what do we have? We have returns of 1000% at no risk. So this is not possible. On the so the combinations risk and return on the right hand side of the frontier are feasible. Okay, so the frontier is the best possible points we can achieve. Okay, given the available markets, assets in the portfolio. So what should we do if these are all the risky possibilities we have access to? Well, we should take, among all these possibilities, we should select the one with the highest Sharpe ratio, and this is the portfolio we should combine with the risk-free rate, giving us access to all the combinations on this line here. Okay, and I'll continue this in the next